Yeah, yeah.
Did you guys just draw those these dynamic? Did you guys do some example on dynamic programming?
Yeah, with the 2 algorithms we did.
You didn't done any examples, right?
We did for the 2 algorithms.
Okay.
Waterman and Needleman.
Okay, then fine. Right. Then we have this. I want to. Then you did this substitution matrix. This Blossom 50 thing. No.
We haven't
No.
done Blossom 50.
Oh, okay. Okay, then so that's the basic idea. I just need to go on, right? Then can move on to our today's lecture, right? Hope you guys see the screen, right? Then in basic idea of this multiple sequence alignment is sometimes we want to align more than 2 sequences, right? So that's the meaning of multiple, right? So in these learning objectives as you should know what is multiple sequence alignment, then what are the uses of multiple sequence alignment, then what are the methods, right? So, sum of pairs, progressive, iterative, log-based. We are just try to give you some overview idea of these things, right? So then so multiple sequence alignment basically mean we should have more than 3 sequences, right? DNA or protein sequences, and we try to align these sequences by introducing some gaps, right? We add some gaps and try to align these sequences. So our goal is to get some greatest number of similar characters for one column, right? If there are several columns, right, there are thousands of columns, we should have to get the greatest number of similar characters for all the columns, right? So that's our goal. So same as the pairwise alignment, right? In pairwise alignment we have only 2, right? So it's similar to two sequences, right? Suppose you have some sort of a set of sequence like these, right? Then you should have you try to get some like this. So this we have W all over this place, right? Likewise, we should get I barely can draw on this one, but so basically you have to get some like this. You have to get most of the similar characters on the greatest number of columns, right? Then so there are some right, so there are some tools. So we're not going to discuss those tools in this course, but to get an idea, so this is some kind of a tool. So you can see that there are some green areas. So green areas means these are preserved in these all through these sequences, right? And these are some gaps, so like that. So are you guys okay up to this slide? So I'll take it as yes, okay. Then suppose you have so if you consider the similarities between these multiple sequence alignment and pairwise sequence alignment, suppose you know this Homo sapien, right? You know Homo sapien, then if there are any bio guys, IS people, do you know what is this species? No? So it is very familiar one, right? So so this is mean
Chimpanzee.
Sorry?
Chimpanzee.
Chimpanzee. Did you Google it?
Yes.
Okay. So basically, so if we consider two sequences like these, like if we show like these some preserved ones, but there are no significant, right? It's just preserved, right? But the case is different if we have it is preserved in so many columns, right? So that photo will be this chimpanzee, right? So if we do multiple alignments, then if you see some sort of like this, we can get some idea about. So these columns are preserved on all these sequences, all these species, right? So that is the most prominent thing on this multiple sequence alignment, right? So this if we consider only two, right, it just some two columns, right? Just one column, right? So but if we go through all these these sequences, so we can see that this whole sequence is preserved in all these species, right? Then I'll show other species also, right? Then so this is what this is mean. I don't know how to pronounce it, right? Macaca, whatever. Then canis, right? Canis means dogs, right? Then this was Taurus means this cow. Then mus, I don't know how to pronounce this. So this is the basic idea, right? So if you want to go through some sort of a set of a sequence alignment, and we can check whether these some sort of these some DNA parts are preserved on all the animals, right? All the animals, all the whatever, it can be a plant or anything, right? So then, so we call this if we have something like this, right? If you consider this kind of these three sequences, we can see that these Q and the PG are conserved, right? Through all these four sequences, right? So we call this as a conserved region, right? So this conserved region means we can tell that there are some homology between these some similarities between these sequences, right? Then we call these type of things as conserved residues, right? So to identify homologous residues, we can greatly facilitate by multiple comparison. We can do multiple comparison and find those homologous areas, right? Then so we can get idea about structural and functional constraint, right? It can be a structural one. It can be some sort of a thing about bond or something like that, or otherwise it can be a functional thing, right? It can be some kind of a functional mean like what that part doing, right? That if there is some kind of a amino, some kind of a acid, so what is that the purpose of that thing, right? Like that. Then so basically these as the usages, we can identify the conserved sequence patterns on set of a sequence family, right? As I said before, right? Then we can these conserved regions are performing. They are telling these things have performing have similar functions, right? Similar functionalities on even in the divergent species. That's the point we want to discuss, right? So even if we consider like the previous pictures, right? Even in the different divergent species, there are some conserved areas, right? Even they are divergent, they have some conserved DNA patterns in their DNA sequence, right? Then these functionalities, these amino acid can be identified in a protein. We can align protein sequences and identify these amino acid conserved. There are in amino acid, the functional and these structural things, right? Then in the phylogenetic analysis, this is the first thing we done in the phylogenetic analysis. We first done some multiple sequence alignment. Then we going to do the phylogenetic analysis, right? Then also we can create profiles, right? We can create some profiles to search some sort of databases. We can create some profile based on these multiple sequence alignments. Okay, someone in the IS people don't have access to this part of the. What do you mean by this part?
As in like they are not available. The whole section, this particular part is not available in the VLE for IS people, it seems.
So can you wait, give me a second.
Sure.
Okay, so can you guys send this link to IS people? I didn't know that there are two course pages for this.
Yeah, IS people are already here, but the
Already
problem is
here. So okay, I'll put the same content on uh, those course pages also, right?
yes,
Just
as in
just send that link to your WhatsApp group, then they can get
sure, we'll do that.
Then shall we wait for some minutes? I feel guilty again.
ISI ඉන්නවා මේ අර මේක තමයි ඒගොල්ලන්ට assignment එක පේන්නේ නැහැ කියලා තමයි කියලා තියෙන්නේ.
මොකද?
activity එක මොකක්ද ඒකට access නැහැ කියලා කියලා දෙන්න.
I look into that one. So
Yeah, sure.
okay, then shall we move on? We have around 45. That's why I asked that participant 45. Then I just see that CS course. Okay, then so we can create some profiles, right? We can create some profiles based on these protein families. We can do some multiple alignments. I'll show you those things at end of this lecture, right? Then we can use those profiles to search to these databases, right? So this is, as I said before, this is the starting point of the molecular evaluation, right? So first we do some multiple sequence alignments, right? Then we find the most similar ones, right? Like this, if we find these two are most similar, then we can, right? If we find these two are most similar sequences, then we can put those two at some kind of a point like this, right? Like that, we can go through this evaluation process by looking at this pairwise alignment similarity score, right? So if we can see this, the point of those evaluation is sorry, right? We can see this, what is the point of these 2i splitting, right? Like that, we can do those analysis based on this molecular, this MSA, right? Then right, then others are, I already mentioned. We can identify the conserved sequence regions, right? Those are functionally important. Then some construction profile for that database searching thing. Then we can predict structural features like some sort of these bonds, loops, like those these structural features in these molecules, right? We can predict those things based on these multiple sequence alignments. So are you guys okay up to now? How about size, guys?
Yes, sir.
Okay, so how about our guys? So if you have any questions, you can ask. We can. So shall I move on then? So then, if we consider this multiple sequence alignment problem, right? There are several solving methods, right? We can do simply that we can do global optimization. That means we can do some dynamic programming. But the thing is, we have to spend exponential time, right? Then we can go for like approximation algorithms. We can get some sort of approximate performance, but in polynomial time. Then we can have some heuristic methods, but those are not performance not guaranteed, but we can get some sort of uh, solution in polynomial time, right? Then we can have some probabilistic methods also, right? In our course, we're going to discuss dynamic programming, of course, right? So in dynamic programming, you have that idea that we try to get the maximum score for a function, right? So the thing is, in the dynamic program, we have that thing is very computationally expensive, so we have to look for other methods. Then we can go for like global progressive alignments, right? In that part, we just get some closely related sequences, and we try to uh, increase those alignments, right? Number of alignments. I'll get into that later. Then we do iterative alignments. Then like local alignments, profile blocks pattern. So basically, in today's lecture, we're going to cover that. We're going to show that this dynamic programming is not going to work on this. It obviously works, but in we consider the running time, so it's not it very computationally expensive, right? Then we're going to do some heuristic, some greedy approaches to do this multiple sequence alignments, right? So if you consider this dynamic programming, so you guys already done the pairwise alignment, right? We can do the same thing for this multiple sequence alignment also, right? Suppose we have some sort of a sequence like this. We have 3 sequences, so we can do the same thing as we did for the previous pairwise alignment, right? The thing is, if we do this in suppose we have three sequences, that means we're going to work on a 3D cube, right? If we have two sequences, we working on a plane, right? We have, if we have 2 sequences, right? So we are working on a plane, right? We put one sequence and the other sequence like this. But in the, if we align more than, suppose at this point I'll talk about three, right? So so you can imagine the 3D. You can imagine it on 3D, you know, right? Then the thing is, if we do the same thing on the in dynamic programming, right? You have to work on a 3D cube, right? So you should go from some sort of a source to sink. You're going to get the maximum value throughout this alignment, right? So suppose you have these three sequences, right? You can arrange these three sequences like these, right? Then you can put it like this. You can tell this is the x coordinate. So this is the x coordinate. This is the y coordinate. And this is the z coordinate, right? Like that, right? So the resulting path will be right like this, right? 0 0 0 0, then 1 1 0, then 1 2 1, 2 3 2, 3 3 3, 4 4 4, right? It is same as the 2D pairwise dynamic programming thing, right? So the thing is, so in a 2D graph, we are working something like this. We have some sort of a line, right? We are working on a line, right? We have this 2D plane. So this alignment is it's like a just one line, right? But in the 3D cube, we have that this one line is changed to a plane, right? Suppose in the 2D manner, we have 3 edges to reach one each unit, right? In 3D cube, we have 7 options, right? Right? Can you see the 7, right? So this is 1, 2, 3, right? So this is one plane, right? This is one plane. Then again, we have another plane here, right? 1, 2, 3, right? So this edge is same for all both these sequences, right? So this is another plane, right? Then this is another the plane, right? So you have 7 edges to each unit, right? Are you clear this point? In 2D plane, we have only 3 edges. We have 3 options to reach one unit, right? But in 3D one, if you align 3 sequences, you have 7 edges, right? You have seven options basically, right? So these are not one line; these are some sort of a plane, right? I'll show you those things later, right? So the architecture will be like this. If this coordinate is ijk, right? So this point is I minus jk. This is I minus jk minus 1. You know those things, no? It's just the architecture, right? Suppose so. If we did something like this, suppose we have so these are our 3 sequences. One is here as, then this is asn, then this is vsns, right? If we do the dynamic programming, so it will draw some path throughout this cube, right? It in 2D plane it is just a one line, but in here it is a plane, right? So the resulting alignment is this, right? So I just put that thing here. Otherwise, it will some sort of a hard thing. So our resulting path is like this, right? So you have V, right? V. So this is this is a gap. Then S. So there are S here. Then N, right? Then A, right? Then we have this AS, right? So this is a 2D motion, right? Can you guys try to imagine that one, right? So it is go through 2 dimensions, right? So this is another dimension. So it from this surface to some sort of this middle point, then this to this backside of this cube, right? Like that. So this is some sort of a plane. Right? So if you check the projection of this alignment, right, we can see some line, right, like this, right? So this is the right hand side. If you look from this side, you can see some sort of a line like this, right? Like that, we can see this cube from three projections, right? This is, try to imagine yourself, right? It really has to show this thing on 2D image, right? So this is one dimension, right? Then this is another dimension, right? This is another dimension, right? Right? Are you guys okay up to now? Can you guys imagine this thing? No? Aish, how are you doing? Aish? Okay. Buddhi,
Yes, sir. I can imagine.
okay. Right, so
Yes, sir.
Sorry, my computer was stuck.
okay. Right, so try to imagine this thing, right? It's same as the 2D plane, right? In here we have 3D cube. That's the difference. In I'm not good at drawing things, but try to do something like this, right? So in 2D we are working on some kind of this kind of a plane, right? But in 3D alignment, if we have three sequences, we are working on a 3D space, right? So multiple sequence alignment is more than three, right? So more than three, you can actually imagine that one, right? That's why I get only three sequences, right? So that's the idea of how these things work actually. So those are not necessarily important, but just you have to get some idea, right? So in dynamic programming, so we're going to maximize this function, right? We're going to maximize this function, right? In 2D pairwise alignment also, you have this kind of a function, right? Same as that, we have this kind of a function, but we are not actually going to discuss these things. We are try to get some idea about these things, right? Running time. Basically, how about IS people and science guys? Do you have any idea about running time of algorithm?
Yes, sir, somewhat about time complexity.
Okay, time comes. So, how about IS people? So, if you're not going to talk, then this session will be stretched up to 8 p.m., right? So, do you want a clarification about this running time complexity?
Yes, sir.
Okay, right. So this time complexity basically means, right, if you have some algorithm, right? Suppose you have some high-end computer, right? So you're going to do some calculation. Suppose you're going to add some two numbers, right? Right. So the time that consumed for a supercomputer or a high-end computer will be very long, right? But if you use some sort of old one, right, it will like around 90s, say 80s, some sort of a computer, right? That will take some seconds, right? So running time basically means it not depends on the your infrastructure, right? That not going to depend on, that's the some sort of a value, right? Some sort of value that's not depend on your PC or computer. It's just how your algorithm works, right? Right. Suppose now like this, if you have some two loops, right? Suppose you have to get some summation or whatever thing on two-dimensional array, right? Whatever thing. So you have to iterate through, suppose you have to iterate through all the elements on this kind of array, right? Right? If you go through one time, right? So you just suppose the number of elements is n, right? So the running time will be n, right? Suppose you running this on another loop, right? So you running this thing on another loop, some kind of, you have another array, right? This is two-dimensional, right? If you run through this one, so you have to go through each element, right? So you have to go through each element, and again you have to go through other element also. So that will be n squared, right? Like that. I'll give you a proper example later. So also you can go through try this link also, right? So in here, so basically I want to tell that, right? So just get an idea, right? So if we have three sequences, right? If we have three sequences n, so the length of this sequence is n, right? If you run this multiple sequence alignment in, right, we have three sequences now. So it gets some time, some kind of, suppose this is some kind of a time, right? You can consider this as some kind of a time, right? So the runtime for this one is 7 and 3, right? 7 comes from, we have 7 edges. We have to go through 7 edges, and we have our sequence length is 8, right? So in our this big O notation, there is some sort of thing called big O notation, right? So in big O notation, we simply remove these constant values, and we get only the n part, right? N part means this is depend on the length of the sequence, right? If we, so you can have the n must be n, right? So the sequence length is 1, you have only one character, right? Also this can be around 10,000, right? So the time that will take is grow depend on the number of characters in this alignment, right? This sequence, right? Suppose you have only one, so n is 1, so it will quickly execute, right? But if we have 10,000 characters, it will take some time, right? That's the idea. So this running time is it depends on the input size, right? Input size means this length of this sequence, right? Just keep in mind. So this is some kind of n to the power 3 something, right? But in the, so if we consider more than 3, right? If we consider k sequences, not just 3, if we consider we have k number of sequences, right? So by this thing, you will get some kind of a value like this, right? 2 to the power k, that means we get 7 from 3, no? If you have 3, you get 7, right? If you have k numbers, then 2 to the power k minus 1, right? Then you have something depend on this sequence length n and the number of sequences, right? In here you have 3 sequences, that's why you have n to the power 3. Now here you have k number of sequences, now you have n to the power k, right? After you solve this one, you get up to something like this, right? We call this exponential running time, right? That means this is not a very good algorithm, right? That basically be something like O1, right? Or log n, right? So these are very smaller than, what about this thing, right? Nk or whatever, n squared, all those things, right? So that is the basic idea. So you should have some sort of a basic idea about how this running time complexity works, right? So for that you can refer this link, right? I'll put some some GIF or something like that, so you can get some idea, right? Right, just keep in mind, I'll give some clarifications later, right? Then okay, then if we get an example like this, right? Suppose we have 6 sequences, right? So our calculation, so this is the thing, we get the number of calculations, right? Time complexity, right? Suppose we have 6 sequences, right? That means 2 to the power 6, right? Then suppose we have sequence length is 100, right? That means n is 100 and 6 sequences, no? And 100 to power 6, right? That means we have to spend this much of calculation to get our value, right? We can get the exact value, but we have to spend more time, right? Suppose we have some sort of if we can get this thing like in n time. N time means we have it just depend on the number of elements on a sequence, right? So for this one, it is 100 calculations, right? If we can get our value in this manner, right, in ON time, so we have to do only 100 calculations, right? It basically tells it is faster, right? Right? Are you clear up to this point?
Yes, sir.
Okay, so so the conclusion is, so dynamic programming approach is we can get the exact value, we can get the optimal value, but it has an exponential running time, right? So that means this is not a very good approach, right? Suppose we have to align 100 of sequences, right? So this thing will be something like this. So if we plot this thing, so this is exponential. That means this thing grow up based on this k and the n, right? So if we increase the n number of elements on a sequence, so the time complexity will be get higher like this, right? In exponential time, right? Then if we increase the number of sequences, the same thing. Suppose we want to align 100 sequences, the same thing happen, right? So basic idea is this is not a very good approach in the time complexity perspective, right? Then for that we have alternatives. So the first one we can have like suppose we have these kind of tree sequences, right? So we can get the inducer sequences, right? We can get like this, right? We can get, so we can align pairwise, right? X, Y, X, Z, and Y, Z, right? We can do the pairwise alignment like you already did on the previous slides. Then we can get, based on these things, we can get we can do the multiple alignment, right? The whole thing, right? So if you suppose we have 3 arbitrary pairwise alignments, right? Then actually, can we construct the multiple alignment based on these inducers one? Suppose we have XY here, right? So the X is ACC, we have one gap here, right? Then another X, right? The thing so basically what we going to do is we have right? We have some sort of sequences, right? Like this without these, suppose without, we don't have any gaps, we have some sort of these sequences, right? We're going to align pairwisely, right? First XY, then YZ, then XZ, right? So in here, right, if you align X and Y, so it has some sort, so we introducing gaps now, right? We have only one gap here, right? Then again it's for only XY, right? If we align X and Z, right, we have to put two gaps to optimize this pairwise alignment, right? Right. So it's the same sequence, but we have different alignments, right? Right. So this is same for this one, right? If you consider Y, we have gap here, right? But in the XY alignment, we have gap here, right? So these two is not the, but same sequence, but different alignment, right? So our goal is to do the same alignment for all these X and Y's, right? Then get the multiple sequence alignment, right? So if we consider this one, right? Can we get this? Can we get the multiple sequence alignment all the time, right? Like we do the pairwise alignment, right? Then we try to get the multiple alignment. Can we do that thing all the time? I guess confused. I give an example, right? Then that will works, right? So I'll do the example there, right? The answer is not always because these pairwise alignment may be not consistent, right? Right? Consistent means you have X as this, right? One gap here. Again, you have same sequence, but you have two gaps here by aligning X and Z, right? So we aligning X and Y, we get a different alignment in these two, right? If we can get the same alignment for all these three pairwise alignment, then we can combine these three, right? Then we can do the these multiple sequence alignment. It means X, Y, Z, all three alignment we can do based on these pairwise alignment, right? That's the basic idea, right? So this idea won't work, right? Sometimes it works, but always we cannot guarantee this thing works, right?
Sir, when
Yeah.
does it work? I don't actually understand when it works.
Okay, I'll give you example. Right? It works like this, right? Suppose you have some sort of sequence like this, right? You have 4A's, 4T's, then 4T, 4T's, 4G's, then 4A's, 4G's, right? Then if we align these three, right? If we align this and this, then this and this, then this and this, right? Right? If we align these, right? So we can build some sort of a triangle like this, right? If we align these two, right? These 4A's and 4T versus 4T's and 4G's, right? So we get the alignment as this, right? We have three gaps at the end of this thing, then three gaps at the beginning of this thing, right? Then suppose we going to align these two, right? So that alignment will look like this, right? Then these two, right? So that alignment will look like this, right? You can see that the same alignment is consistent, right? So we have 4A's, 4D's, and three gaps, right? It's same in this place also. Then if you consider this one, three gaps at the beginning, right? So it has the same alignment in this place also. Then the final one, 4A's, three gaps, and 4G's. So it is same in this place also, right? Like this kind of a thing, it works, right? So basic idea is it works sometimes, but we can't guarantee it all the time, right? Are you clear? No?
I think so.
What is your question actually? So that's the you have to think like this. So we can't actually enforce. So there are several sequences. No, we can actually imagine that thing, right? So there may be some things that works like this, right? That's the basic idea. There are some sort of alignments that will agree to this thing, this method, right? We can do pairwise alignment, right? That will basically consist that alignment on the other. If we align the another two, so this thing will consist, right? So this alignment is consist on the alignment same as these both these alignments, right? So you can actually do this one, right? You can do this one and check whether it actually works, right? For then as another question, right? I just want to give you this thing as the activity, right? Give you small activity, right? We have around 30 minutes to go, right? So just try to do this one, right? You have 4A's, 4T's, 4T's, 4G's, and 4G's and 4A, right? Try to align these three like this one, right? You can align this one and this one and this one, right?
So I have a small question.
Yeah,
Here we are aligning 3 sequences now.
yeah,
So in pairwise alignment, there is some penalty for gaps, and
yeah,
it's
yeah, yeah,
better it's better
yeah,
than the aligned one.
yeah. That's based on the scoring method, right?
Yeah. Here we align for 3 sequence now. So
Yeah,
I think the as it aligned,
yeah.
are there any more
Constraint.
value? Sorry,
You mean the more constraint or something like that?
no, more value here because it's aligned 3.
No, actually, our method
Column?
is we actually try to it just some kind of a greed, not a greedy, but some kind of approach. We try to, so we can do this pairwise alignment very easily, no, right?
Yeah,
Right. We try to do the if we have 3 sequences, first we try to align these by pairwise, right? If this alignment is consistent, then we can put this, we can write this one, our multiple sequence alignment, right? We
yeah,
can write, so this is same, no, right?
yeah,
This thing aligned with this one, right? So this thing are all these alignments are consistent, and this thing is aligned with this one, right? Then suppose we can get this one. So this thing is aligned with this one, right? We
yeah,
can simply write this one also here, right? Did you get the idea? Right?
yeah.
So
I asked.
something is aligned with something, right?
Yeah,
So that thing also aligned with another thing, right? So we
yeah.
can write something like this, right? So what is that scoring method thing?
Here I asked the question because I as just look, I had some answer like 4 A's,
Okay,
4 T's, and 4 penalties or 4 gaps.
4 gaps, right? You mean another gap in this place?
Yeah. Then for second one, it's beginning 4 gaps, then 4 T's, 4 G's, and the last one 4 A's, 4 gaps, and 4 G's.
Yeah, that maybe works, but that based on your that scoring method, no?
Yeah,
So if you continuing one gap is you in here you continuing one gap, right?
yeah,
In here you introducing one gap, right?
yeah,
Those two are very actually, we know that introducing one gap is very, we rarely do that one, right?
yeah,
I think because of that scoring method, that's why they come up to some kind of this solution, right? That basically depend on the your scoring method, right? That pairwise alignment depend on the scoring method, right?
yeah,
Right. If you introduce another gap, so that score will be low, right?
yeah,
So you can have a better optimal solution for that one. So we should go for the better optimal solution. Right?
Yeah.
Right? Are you clear?
Yes.
Okay. So as I'll give you a small question, right? So this is the question, right? You can simply write like this, or you can, if you can draw, that's fine. You can draw on your some sort of a paper, or you can get a snap and submit, right? Otherwise, it is okay to just type these values, right? If you align these two, what are the values you get? Then these two, what are the values you get? And these two, right? Like that, can you do that one quickly around 10 minutes? I'll already uploaded, I'll already open a link for your submissions, right? You can check VLE for IS people. I'll put the link, right? Try to do this activity and tell me whether that's fit with this multiple sequence alignment or not, right?
So is there some kind of rule like we can only have
Okay.
6 steps for 2 sequences or something?
Okay, we'll go in this way. So, as the scoring method, right? We can have -2 for introducing a gap, then -1 for continuing a gap, and -1 for mismatch, right? Right? I don't know whether it's work, but let's see. And this one for opening gap, then this one for continuing gap, right? This one for mismatch. Those are minus values, right? For matches, we can give around 4 matches. Shall we give one? Let's see, right? Try to do the pairwise alignment, then check whether you can combine those things, whether those things are consistent throughout these alignments, pairwise alignments, right? So values are 1, -1, then -1 for continuing, -2 for opening, right? Did you guys do some examples on the previous lectures in pairwise alignments?
We did for some algorithms.
Okay. What do you mean by algorithms means actually?
Local alignment and global alignment.
Oh, okay. Okay. you can do the local alignment, right? So you can introduce more, you can introduce gaps and try to optimize try to get the max value for each pairwise alignment. I'll give you 5 more minutes, then we can get into the lecture. Yes, people, can you guys check the VLE whether your link is visible? If the link is not visible, just let me know, okay? Okay, shall we start? So I'll extend your deadline, right? Then you can submit it, right? So, right. So the idea was, so if you try to align some kind of a sequence like this, right? If you do the alignment, right? So you have to get the optimal solution for your pairwise alignment, right? You are not considering the whole thing, right? You are not considering the these tree of sequences. You just considering these two alignment, right? You just try to get the optimal alignment for these two, right? So the one answer is like this, right? You have 4A's, 4D's, and 3 gaps, right? Then if you align these two, right, you will get some sort of something like this, right? So you can see that this is not consist with it's different, right? This alignment is different. We have 3 gaps here at the end. In here we have 3 gaps at the starting point, right? So it's same for other two also, right? I just want to tell you that this method will not work always, right? At some point we can get some sort of answer, right? We can get we can do a multiple sequence alignment, right? But we can't guarantee based on this approach, right? Are you clear with that, right? So the thing is, this has a different alignment than this one, right? But the same sequence, right? So based on that, we can write like the previous one. But in the previous one, we have this this alignment here, right? We can write that one. Then this thing aligned with this one, and then that one, right? Then this thing is aligned with this one, right? The third one, right? We can finally get the multiple sequence alignment, right? But in here, that is different, right? You can you have different alignments, right? So if you write these two, but you can get another one from these two, right? So triple 4A, 4D, and three gaps. So this is different from this one. Then 3 gaps, 4Ts, 4Gs. So that's also different, right? So you can get a multiple sequence alignment based on this one, right? Are you guys clear? Right? Then so I want to highlight this point, right? Someone asked that thing, I guess, right? That previous question, right? If we try to get the optimal multiple alignment, right? If you focus on our optimal multiple alignment, that means suppose we have 5 alignment, 5 sequences here, right? If you focus on this one, right, we can infer the pairwise alignment, right? We can get those pairwise. This can be a pair, this can be a pair, like that. We can infer, but right, if we check those pairwise alignments, right? Suppose if we take this and check, right? These are not necessarily optimal, right? Right. So this is the idea that we can get the multiple optimal multiple alignment but necessarily that these pairwise alignment are not necessarily optimal, right? Right. There may be good better alignment in these two pairs, right? But if we consider the whole picture, we don't need to optimize the this alignment, this pair, right? We don't need to optimize this one, right? We go for the whole picture. We go for the all the sequences, right? Then so it is actually difficult to infer good good multiple alignment based on the optimal pairwise alignments, right? If you try to get the optimal pairwise alignments and then try to get the optimal multiple alignment, that won't work every time, right? So that's the basic idea I want to highlight, right? If you don't get this, just tell me, I'll explain again, right? It's some kind of like a NP complete problem, right? You can simply, if you have the optimal solution, you can tell that these are the pairwise alignment, right? You can easily tell that, right? But even if you can infer those pairwise alignment, if you check those if you take these two alignments, if we check these two alignments, so these two are not the optimal solutions, right? There may be another some sort of alignment that will have more value, that means more score than these two alignments, right? Right. But if suppose we are looking for the best multiple alignment, we not going to get the best value for the pairwise, right? We not considering the pairwise alignment, right? In the other hand, we can't go for a good multiple alignment from a optical pairwise alignment, right? If we done a better job on this pairwise alignment, but still it is hard to go for a good multiple alignment, right? If you try to, suppose you have this sort of 5 sequences. First you get all the you do all the pairwise alignment and get the best score for all the pairwise, right? Then if you try to go for this better, that optimal solution for multiple alignment, so that won't work, right? Are you guys clear with that one? How about IS people? I think it's better you guys talk, otherwise you will this will affect your GPS, right? If we ask some sort of a question from these things, so that if you didn't get the idea, so you can't actually write the answer, right? So this is the final semester, right? I think it's better to, and the science faculty also, right? I'll do that logic programming thing. You guys are not going to talk now, right? So it's better if you have any questions, just ask, right? So we are considering two different things, right? We considering optimal multiple alignment plus this optimal pairwise alignment, right? We can do, so our goal is to get the optimal multiple alignment, right? So if you go for that one, suppose you finally get to some sort of optimal multiple alignment, right? Then if you check whether these, if you take some two sequences and check, right? You can see that there are the optimal solution for that two pairwise alignment, right? If you do the pairwise alignment for these two sequences, you can see that there are optimal solution other than this, right? So that's the idea of this one, right? So that means we don't need to necessarily optimal the pairwise alignments, right? So on the other hand, right, if you go for, so you're going to do a better job on pairwise alignment, right? So you're going to get the better values on these pairwise, right? Then you try to get the multiple sequence alignment, right? So it's not going to work, right? So that won't be your optimal solution, right? Right? So you have to, so you had focus on this one, right? You have to get the optimal multiple alignment, right? So that previous approach is not going to work, right? Right? I'll suppose you guys understood that part, right? Then this profile representation, right? Did you guys do this profiling thing? Profiling the based on some sequences?
No.
No. Okay. So in so profiling is some sort of getting some probability, right? So suppose you have some sort of these sequences, right? If you look at the sequence, right? So I start from this one, right? You have five ways at this column, right? Right. So you have some set of sequences, right? You have some set of sequences, and you have to align with this sequence, right? if you check on that one, right? Suppose then for if you take A, right? So what is the probability of A occurring at this column, right? If you check all these rows, right, you can't find the A, right? So that means the probability of A occurring at this column is 0, right? If you check this place, right, you can find all the values are A's. That means the probability is 1, right? How about this place? We can't find any A's, right? 0. Same for these, right? Like that. Then again, 1, right? Like that. For some kind, if you find something like this, right, you can find 4 A's in this column, right? That means A will occur at this. If you number these columns, the probability of A occurring at this column is 0.8, right? Like that, you can generate some probabilities, right? So then the next one, if you consider C, right? So C, we have five rows now. We have 3 C's here, 0.6, right? Then again 0, 0, 0. And again we have all the C's, all the values are C. Then 1, right? Like that we can generate some probabilities, right? So then based on that we can align based on those probability values, right? I think that I'll ask that Ms. Amal to cover those part. So then that will be more clear to you guys, right? Then so in the previous lectures you already done this sequence alignment, right? So now we're going to align sequence against profile, right? Then the profiles again profile. So what it means, right? Like this. If you have given 2 alignment, right? Can we align this, right? You have three sequence in this alignment and 2 sequence in this alignment, right? If you want to align these 2 alignments, that means element 1 and element 2, right? You can simply combine these alignments, right? You can combine these alignments and do these profiles. You can generate that probability values, right? So are we going to use that in multiple sequence alignment? It's like this, right? So suppose you have right. Suppose you have k number of sequences, right? Suppose 10. You have 10 sequences, right? So what you're going to do is, so you're going to first do pairwise alignments, right? Right? Do all the combinations, right? You can have U1 plus U2, U1 plus U3, and you do all the pairwise alignments, right? Then you check what is the most similar sequence, most similar to sequence, right? Now here U1 and U3 are the most similar ones, right? If you check A is here, C is here. For this column you have 2 options, G and T. For this column, remove this one, right? Then for this column you have T and A options, right? Then A and C, C and T, like that. You can have options, several options for a column, right? Like this, right? Then you can combine this U1 and U3 into 1, right? That we call as profile, right? So in here you can write the same thing, right? U1 and U3, first element is A, no? You type A, then second element is C, then C. For third element you have 2 options, right? G and T, right? Then again T, A, C. Again you have 2 options, like that. For suppose you have 10 alignments here, right? After you done pairwise alignment and find the optimal one, you can write this U1 and U3 as this U1 U3 profile, right? That means you reduce this 2 alignment into 1, right? If you have 10 here, then you have 9 here, right? Because the one is a profile, right? others are the same, right? Again, you do the same thing. You do the same pairwise alignment, right? So this is a greedy approach, right? I'll show you some example. Right? Suppose you have 4 sequences, right? You have this kind of sequences here, right? S1, S2, S3, F4. Then you have 6 possibilities. No, you can have S1, S2, S1, S3 pairwise, right? S1, S2, S1, S3, S1, S4, S2, S3, S2, S4, like that, S3, S4, right? Like that, you can have 6 possibilities, right? That means 6 alignments you can have, right? Then you're going to do the pairwise alignment, right? You select pairs, right? Like this, you can select 6 combinations, right? Then you do the pairwise alignment, right? Like this, right? So the score will be generated based on the your this match mismatch gap based on that matrix, right? So you generate some sort of score based on your matrix, right? Then you check. So this is the first iteration, right? So this is the first iteration. You have 6 possibilities, right? So now you align these 6 sequences, right? Then you check the score, right? So this thing has -1, 0, 1, 1, and 2, right? So you get the highest score from S2 and S4. Then you can tell that S2 and S4 have more similarities than other 5 pairs, right? Are you guys clear? No?
No, sir.
Sorry?
I couldn't understand.
Okay. So it will something like this. I'll start from the beginning, right? So did you understand how the algorithm works?
Yes, sir.
Right? You combine most similar 2 pairs and put it into one, right? So that's the algorithm, right? So if you run this example, right? So you can have 4 possibilities. You can have 4 pairs, right? So that is okay. No? You can have S1, S2, S1, S3, and S1, S4. Then these 2, then this one, right? 3, 3, right? You can have 6 combinations, right? So yeah, go ahead,
Yes, sir.
right? Then what you're going to do is right? Then you have those pairs, right? So still you didn't align those things, right? You have these 6 pairs, right? Now you're going to do is you're going to take now you're going to do the pairwise alignment, right? You take S2 and S4 and do the pairwise alignment, right? For pairwise alignment, you have to get this corner. You can define those values, right? So I'll give, for match, I'll give 1 or 2. Then for mismatch, I'll give -1. For opening gap, -2, like that. Continuing gap, -1, like that. You assign some values, right? Then you try to get the optimal value for each alignment, right? Each sequences, right? Based on your defined set of values, right? So this one is S2, S4, then S1, S2, S1, S3, right? Different sequences, no? Different sequences are aligned, and you check what is the most similar one, right? So how are you going to find the most similar one? So you find the most similar one based on your score, right? Right? So you check this one, it has minus score, right? That means those 2 are not much similar, right? Same for this one. This score is 0, then 1, 2. By looking at this, you have the highest value by S2 and S4, right? You get the highest score by aligning S2 and S4, right? By looking at these 6 possibilities, right, you can tell that S2 and S4 are the most similar ones, right? Out of these 6, you can tell that S2 and S2 and S4 is the most similar to sequence, right? Are you okay up to now?
Yes, sir.
Right? Then what you're going to do is, so you have these different mismatch items now, right? As I said before, you can make the profile now, right? So S1, S2 are the closest one. Then we combine those two together, right? Right. So these are two sequences. We combine those two together, right? We call this as a profile, right? For in the profile, right, we have some similar values like right in this way, right? If we have several options for one column, then we write TOA like that. Right? Those mismatch options are right on this way, right? So this is what we call profile, right? Like that, we can substitute this whole multiple sequences into a one profile, right? You can get a one profile. Suppose you have 10 sequences, you do this algorithm 10 times, right? 10 or 9 times, then you get the one profile, right? You get the one profile. It has S1 to 10. You can name as S1 to 10. Then you have these values, right? You can have, if G is conserved on all the 10 sequences, so the G will write it as G, right? Then suppose you have 2 options for second column, then you can type TO, whatever the other option, right? TOG, whatever, right? Like that. Like that, you can construct the profile by aligning these pairwise alignments, right? Are you okay up to now? Is it okay? It's just a representation, right? Is it okay? Buddhi?
Yes, sir.
Yeah, go ahead. What's the
Yeah,
issue?
I think some example maybe.
Okay, I'll do the example next day, right? So it's around 7:45, right? So as I continue this example, right? So now you have first, at the first place, you have 4 sequences, right? Those are the 4 sequences. Then after you done one iteration, so these 4 sequences are reduced to 3, right? Because you combining one of them and write it as a profile, right? And then second iteration, start of the second iteration, you have one profile, right? Then 2 sequences, right? Right? So these are the 2 sequences and this is the profile, right? We name our profile as S24. 24 means we combine second sequence with fourth sequence, right? So we name it as S2, 4, right? So this is a profile and these are the normal sequences. Then again we run our algorithm, right? At the end of the algorithm, we get to do some one profile is 1, 2, 3, 4 like that. We get some sort of a something like this with with options, right? If you have several options for one column, you can write it as like this, right? Is it clear? I'll give you an example to do the next day, right?
Okay.
Okay. Okay, then so we call it sum of pairs, right? So this is we consider this as a standard multiple sequence alignment scoring method. So it's we done this by column cost weight function, right? Cost of weight function. We have for a column we have some sort of a weight. What's the possibility of occurring one element, right? Like I previously showed that matrix like that. Then so then we do the scoring based on this substitution matrix, right? So you mentioned that you didn't do that part, that blossom and palm substitution matrix. You didn't do that part, no?
No, sir.
Okay, I'll cover that one. Then so we want to maximize our total alignment score, right? By maximizing each column, right? We get the maximized total alignment. That means we get the optimal solution for MSA by maximizing the score for each column, right? For each column, we try to get the max value. By getting the max value, we finally get the maximized MSA, right? So that's the end of today's lecture, right? So it's almost, I got almost 2 hours, right? So you can submit that, you can do that submission and upload it. Then I'll extend the deadline. Then I want to mention that, so this, since this is the last semester of your 4-year degree, so this subject is a very, actually, you can get a better GPA value on this, better marks on this subject, right? So this scope of this subject is very small considering to the other subjects, right? You can get a better result, then that will boost your GPA, right? If you on the edge, that will push you, right? So if you have any questions, you can ask now. Then also I'll do some small, I'll give you some examples based on that running time complexity, and I'll do that matrix thing, right? So if you have any questions, you can ask now. I think it's better you guys talk in this lecture. And one thing we have around 3 more weeks to go. I'll complete the rest of this multiple sequence alignment on next week. Next week means when we have the lecture Tuesday, no?
Yes, sir, on Tuesday.
Okay. There are some concerns with that. We'll have that. Okay, that will be fine. We'll see. We have that virtual museum thing now. You guys know that one? That since we have completing 100 of years, right? We have some arrangement, I think, right? So we'll try to do the lecture on our Tuesday time slot, right? In this Friday time slot, Miss Amali will do that quiz thing and the phylogeny tree thing, right? So she will complete the phylogeny. Then I'll, as the next 3 weeks of mine, I have to complete this multiple sequence alignment, then hidden Markov models, and finally I'll do some basic idea of neural network, right? I'll try to make it more simple as possible since we have IS people here. How about science guys?
We did machine learning, sir, last year.
Okay. How about IS people? Did you guys do that third year machine learning thing? So,
Some
yeah.
of us did, sir.
Okay, so I'll make it simply as possible, right? So you'll get a question from these teams as well as content from Ms. Samali and Mr. Pool, right? So, okay, then we'll end our session. If you have any questions, you can ask, right? Else you can leave now. Thank you very much.